his entirely theoretical model, so it's not directly related to analytics. But I chose this topic because I want to present in academia, especially people working in theoretical model like me, how to use optimization to describe insurance problems. So theoretical model and application, they are not conflict with each other. So I believe we can find a way to connect them to the real world and the real applications. Okay, so this is the roadmap. I will introduce our motivations and then introduce two models. I will mainly focus on the expected utility model, and then the conclusion is the end. Okay, so to start with, so let's recall what we learned in the first class of insurance. So in an insurance contract, we need to have two parties. One is the risk-averse policyholder who is holding an insurable risk. So the keywords here are risk-averse and insurable. On the other side, we need to have an insurer who has a pool of many diversifiable risks. So the keywords are pool and diversifiable. So the policyholder, because of the risk aversion, the policyholder is willing to transfer his risk to the insurer by paying a premium higher than the expected amount of the loss. And the insurer can accept this premium and diversify this individual risk in the pool of risks. So the risk pooling effect will equip the insurer a stronger risk management ability compared to the policyholders. So the risk aversion of the policyholder in theory can be described or formulated by the expected utility theory, so which is a very elegant theory in economics. I believe all of you are very familiar with that, so I quickly go through all that. So if a person is risk averse, his preferences of wealth can be formulated by a utility function U. And this U normally will assume it is increasing and concave, which means the person wants to be richer, but the marginal utility obtained from one extra dollar is decreasing. So on the other side, for the insurer, the risk pooling effect is supported by the law of large number, which is a very powerful theory in probability. So typically, the law of large number is saying that when risks are diversifiable, or more precisely, when risks are identical, distributed, and independent, then the insurer should be able to predict both the frequency and the severity of losses. So the insurer is not necessary to identify each individual, each losses, but he can predict what is the aggregate amount. And this aggregate loss should be manageable. So more importantly, still due to the law of large number, the more the losses, the more precise prediction the insurer can do. So that means if risks are diversifiable, then the insurer is always looking for more policyholders, more risks, because the more, the better. So up to now, everything looks good, so we have policyholders who are willing to transfer their risks. And we also have an insurer who's always looking for new policyholders. So there is a perfect match between supply and the demand. So, but in the real life, the real world is always sophisticated. So we always need to challenge assumption in the classical model. So in this work, we focus on the concept of diversification. So here, diversification means risks should be identical, distributed, and independent, or close to that. But we can challenge these two assumptions by the practical assumptions. So the first observation is inhomogeneous policyholders. So in this real world, we know everyone is different. We always have our own risk altitudes, wealth levels, and our risks are different in sizes, in variations. And because of that, we all have different willingness to transfer risks, and we can accept different levels of premiums. So policyholders are inhomogeneous. A natural question is, when policyholders are different, should the insurer use personal information, personal characters to select his policyholder and exclude others? And if so, what features or characters will be preferred by the insurer? In other words, for one policyholder with certain character, whether this policyholder will affect the insurer's decision in offering insurance to other ones. So that is the question we want to consider. So the next thing is how we challenge the independent assumption. So independent assumption is a very essential one in insurance merchandise, but in many circumstances we know risks are not independent or they are related. So one typical example is the catastrophe risk. For instance, the Hurricane Katrina in 2005, we know that it incurred more than 1.7 million claims, and the aggregate loss is between $40 to $50 billion. So it replaced the 9/11 attack as the single most expensive incurred operations. So the similar natural disaster will instantaneously incur many losses in one insurance period, and all losses are correlated, so they are far away from independent. And second example is the macro correlation phenomenon. So here I quote one example in Cook's paper in 2010 to explain the macro correlation phenomenon. In this example, authors use the national flood insurance claim data, and the data set covers 20 years and nationwide. So use this data, authors did 3 experiments. In the first experiment, they calculate their correlations between 2 counties and randomly selected. And in the second experiment, authors first sum 100 counties and then calculate the correlation between 2 aggregate risks. In the third experiment, the number of counties in one summation is 500. So all 3 experiments are repeated for 500 times, and then they calculate what is the average correlations. So here is the result. So we can see that the first figure represents the average correlation in the first experiment. So the correlation among 2 randomly selected counties. So the correlation, in general, the shape of the figure you can see is skewed to the left. And the average correlation is very close to 0. So it means there are good dependence assumptions between individual counties. However, if we do summation first and then calculate the correlation, then in the second figure we can see that the shape moves forward to the right, obviously. In particular, when we have 500 counties in one summation, the average correlation between 2 sums is 0.71, and this value is statistically significant away from 0. So this result shows us the macro correlation may amplify the correlation of sum. So this may give us a warning in reinsurance market, because in the reinsurance market, reinsurer is taking the responsibility of the aggregate losses from primary insurance. So even though the individual losses may look very close to the independent assumption, but when the primary insurers aggregate those losses and transfer the aggregate loss to the reinsurer, then the reinsurer should be very careful about the correlations among his agents. So based on those observations, we can conclude that in practice, policyholders are different. They are inhomogeneous, and also risks are not diversifiable. So the question we want to ask is, when these 2 essential assumptions in the classical model are violated, then what is the consequence in the insurance supply from the insurer's perspective? And we ask this question on 2 levels. On the individual level, so when the insurer is offering policies to one particular policyholder with certain characters, whether the insurer should use the personal information to decide what is the optimal insurance coverage, and also whether this decision will affect insurer's decision to other policyholders. On the aggregate risk level, we want to identify what is the optimal size for the insurer. So before, recall that when we have the diversification, we have a homogeneous policyholder, then we know the more the better. So the insurer is always looking for a larger size of pool. But when those two conditions are violated, whether is still true for the insurer. So what is the optimal size for the insurer right now? And if the insurer does not want to have as many as policyholder, then how the insurer choose policyholders? What characters are the critical criteria for the insurer in his decision? So these are questions we would like to discuss in this work. Okay, so next I want to use the expected utility to formulate our consideration. So here is the model setting. For the insurer, we have only one insurer, and with the wealth W0 and his preferences is characterized by the utility function U0. And in this market, the insurer has n potential policyholders. So of course, the interest case will be n strictly larger than 1. And the insurer will offer co-insurance to all policyholders. And in our notation, we'll use alpha I to represent the co-insurance coverage. So alpha I equals 0 means no insurance. On the other hand, alpha I equals 1 means full insurance. So use co-insurance mathematically can give us a more attractable result. And also it's very clear to say what is the coverage level. And so this is the optimization. So for in this objective, so W0 is the insurer's initial loss, and this sum is the aggregate loss faced by the insurer from the entire pool. So this is the insurer's liability. And we use pi I alpha I to represent the premium charged from to policyholder I for the coverage alpha I. So this is the total premium collected from the entire pool. So this one represents the terminal wealth of the insurer after one insurance period. And in the expected utility theory, the insurer wants to maximize his expected utility by choosing the optimal insurance coverage to all potential policyholders. Okay, so in this work, because we only focus on insurance supply, that means somehow we need to make the demand to be fixed. So we will use the premium to control the demand. We need to make sure that this premium can be accepted by policyholders. By doing so, we guarantee the 100% of demand. And then if we observe some zero in the optimal solution, that means the insurer does not want to offer 100% supply. So that means there is insufficient insurance supply exists in this market. Okay, so, but before introduce how we use the premium to control the insurance demand, I want to mention how we formulate the correlations between individual risks. So since we cannot assume they are diversifiable or independent, we need to formulate the correlations. So in this work, we use the systematic risk. More precisely, you can imagine that this systematic risk Y is kind of, for example, a natural disaster or an earthquake. And once the earthquake occurs, it will affect all properties in a certain very large areas. So in this large area, all individual risks will be affected by this same risk event, which is represented by the systematic risk Y. So for each risk, we assume it can be decomposed into one systematic risk component and also one personal component. This personal component, we can assume it is independent from the systemic one, and also independent from other policyholders. So we use the beta I, this parameter, to control the correlation level. So when beta I equals 0, that means individual risk is not correlated with the systemic risk. So it is independent from the market, from other policyholders. That is the most ideal case. However, when beta equals 1, that means individual risk is fully determined by the systemic risk. And by choosing a value of beta I between 0 and 1, we can control smoothly what is the correlation level between the individual risk and the systemic risk Y. And by doing so, we can control the correlation between any two individual risks. So the beta I times beta J will be the correlation coefficient for any two individual risks. So in this work, we'll only consider positive correlation because this is the more interesting case for the insurer or their concern. If we have some negative beta that cannot two risks can hedge each other, then it's too good to for the insurer to assume. So another thing about this formulation is that we keep the variance or standard deviation and the mean of the individual risk to be fixed. The reason is that from the insurance data, the first and second moments are relatively easy to obtain from a given set of data. So the insurer normally has very large confidence to assume what is the average expected loss and what's the variance of individual risk. But the uncertain thing relies in the correlation. So this formulation leaves us benefit us in this way. We can fix the second and the first moment, while we can still control the correlation. Okay, so next is the indifference price. For the indifferent price, this is how we control the insurance demand. So we define the premium is obtained from this equation. On the right-hand side, this is the expected utility for one policyholder without purchasing any insurance. On the left-hand side, this is the expected utility of purchasing coverage alpha. So to make the policyholder accept this coverage, the premium cannot larger than this value because otherwise purchasing insurance will lead to a lower expected utility, which is make no sense for the policyholder to purchase the insurance. So of course, I agree that this is not very practical because in practice it's very difficult to assume, to find out what's this indifferent price. But in our work, it guarantees 100% demand, and also it represents the highest premium can be charged by insurer. So it represents, if the insurer can charge the best price, whether there's still some insufficient supply. Okay, so next is our first result. So typically, so this is general result. How we interpret that? It means combine this. We show this objective is concave, so mathematically we can solve the maximization. But more importantly, that we observe that in the optimal solution for the insurer, no alpha I star should be 1, so no full insurance there. What does that mean? It means if the optimal solution is strictly between 0 and 1, so it's an interior point of this cube, high dimension cube, then that means all policyholders will receive insurance, so no insufficient supply. However, if we found that the optimal solution is achieved on the boundary of this cube, then that means some policyholder will be excluded from this pool because they will be offered 0 insurance. So that is a more interesting situation. So next we get a close look at 2 different cases. The first one is independent, the most ideal case. In this one, all beta I equals 0. So all risks are independent from each other. We can solve what is optimal coverage. So in this result, so AI represents the risk of aversion level for policyholder I, and A0 is a risk aversion level for the insurer. So these two parameters will determine the optimal coverage. And since now there's no zero appear, then on the individual level, we know that all policyholders will be offered insurance policies. And the more risk-averse policyholder will be offered a larger coverage. And on the aggregate level, the insurance supply is 100%. So it's very similar to the classical result. However, if we consider another extreme thing, the perfect dependent case, then this result is totally different. So let's look at the solution. So here we observe some zero. And how we determine the zero? So for the convenience, we assume the risk aversion times the standard deviation is increasing from policyholder 1 to policyholder n. Then the insurer will first identify a threshold. So find some I star such that for policyholder from 1 to I star from 1 to I star, they are not good enough for the insurer to offer policies. So they will be excluded by the insurer. And the insurer will only offer policies for those policyholders who has a larger standard deviation and more risk averse. So here I use a graph to illustrate this result. So in this graph, this y-axis represents standard deviation and x-axis represents risk aversion level. So in this graph, we have 10,000 policyholders. So you can observe that only 63 policyholders located in the right top corner will be offered insurance. So this represents a huge insufficient insurance supply in this market if all individual risks are fully depend on the systemic risk. And if we consider the percentage of policyholders receiving insurance in terms of the size of the pool, we can see that when the size of a pool is increasing from 0 to 5,000, the percentage decreasing very fast. And on the other hand, statistically, this percentage is between the size. This is n to the power 1/2, and this is n to the power 1/3. It's increasing with the size of the pool in this speed. Okay, so these two examples illustrate on two extreme situations. When all risks are independent, then we still have full insurance supply. While if all risks are perfectly dependent, then we will have very severe insufficient supply. And so next, we consider the intermediate cases. So now, by controlling beta, we can control the average correlation among individual risks. So to be simplified, we assume all beta I equals beta. So still, we can have a very similar result. So in this graph, we illustrate when the size of the pool is 50, 500, or 5,000, what is the percentage of policyholder receiving insurance in terms of the correlation level, beta. So we can have some observation. First of all three cases show a clear decreasing trend. So that means when individual risks are more correlated, then the insurer has incentive to exclude a large portion of policyholder from the pool. And if the size of pool is relatively small, like say the 50 policyholder in this market, then we can observe some slight range when beta is close to 0. So it's nearly when beta equals 0.3. That means the insurer is kind of tolerable some small correlations between individual risk when the size is small. So the insurer still can offer the full insurance to the whole market. But this slight range is very small when the size of the pool increased to 500, and it's totally disappeared in the large pool. So that means for the large pool, the insurer is more sensitive to the correlations. Once there is some correlation, the insurance supply will decreasing dramatically. So this is represent that how the insurance supply will decreasing along with the correlations. So this is result we obtained in the expected utility, and we also do the similar analysis for the mean variance model. But because of time, I won't go through that. So in summary, in this work, we consider the insurance supply in an insurance market. In particular, we consider the personal information, like the risk aversion and the risk size, and also what is the correlation between individual risk, how those characters will affect the insurance supply, in insurance decision. So on the individual level, the insurer definitely wants to use personal information to exclude some policyholders to select the best ones. So on the aggregate loss, we can observe that when the correlation is increasing, there may exist very severe insufficient insurance supply in the market. So this will be give us some warning in the especially in the catastrophe risk. So in this kind of catastrophe insurance market, the insurer cannot supply sufficient insurance policies to all policyholders. So in this case, maybe the government needs to step in to support the insurance supply in the market. Okay, so this is what I want to talk about today, and thank you very much for your attention.